In this video, we're going to start getting ready to learn how to add and subtract fractions. So we're going to begin by talking about like fractions. And also finding equivalent fractions. And of course, don't forget to add in your date to follow along and stay organized. So fractions with the same denominators are called like fractions. If fractions are not like, they are unlike. So for example, 1/3 and 2/3 are like fractions, but 1/3 and 2/6 are unlike fractions. Okay. So it has nothing to do with the value of the fraction. If you actually reduce or simplify 2/6, you will get 1/3. So it doesn't have to do with the value because these are actually the same equivalent fractions. It just has to do with the denominator. So if the denominators are different, they are unlike, and if they are the same, then they are like fractions. And why we need to know this is because we can only add and subtract like fractions. This is very much like with like terms, right? So if you think about this, we've been multiplying and dividing with fractions that are like or unlike, it doesn't matter. And it's the same thing with variables, right? We can multiply with variables or divide with variables, it doesn't matter. But when we're adding or subtracting, things have to be the same thing, the same kind of units, the same type of thing. So when we're adding or subtracting with variables, we have to have the same variables. When we're adding or subtracting with fractions, we have to have the same type of fraction, so the same denominators. So that's really important here. Once we have the same denominator, it's easy. For instance, something like 1/3 plus 2/3 is going to be 3/3. So we add the numerators and keep the denominator. And then now we do need to simplify though. So here I can divide these both by 3, or 3 divided by 3 is just 1. And we simplify at the end still. So your denominator may change in the final answer, but to add or subtract, they need to be the same. So for example, let's say I have something like 8/9, and I want to subtract 2/9. Well, these are the same. They both have 9. So I just subtract my numerators, which is 6, and I keep my denominator the same. And now we do have to simplify. So I can divide these both by actually 3 again here, and I have 2/3. Okay, so we still need to make sure our answer is simplified answer in the end. Okay, so once we have those like fractions, it's very quick to add or subtract them. We just keep the denominator the same, add or subtract the numerator, and then simplify at the end. And of course, you can work with negatives as well here. So just to kind of do maybe one more or two more examples. So if I have something like 11, negative 11/15 plus 6/15. Well, you're just going to apply your sign rules. So I have negative 11 plus positive 6 in the numerator, and the 15 stays the same. Negative 11 plus 6 is going to be negative 5. And then I do need to simplify here. I can divide these both by 5, and I get negative 1/3 as my final result. We can also go ahead and subtract fractions using our sign rules too. So maybe I have something like 4/5 minus negative 2/5. So here I see I'm subtracting a negative. So remember with subtraction, what we do is we keep the first fraction the same. We change to addition and we change the following sign. So that negative will become a positive. And now 4 plus 2 is 6. So I have 6/5 here. Sorry, guys. Hang on. Okay. And 6/5 is fine for a final answer. If you do need to have it as a mixed number, you can go ahead and change that over. Sorry, guys. All right, I apologize, guys. The joys of working from home. So 5 goes into 6 one time, which is just 5. So I have a remainder of 1. So 1 1/5 would also be our final answer here. So you just want to make sure you're really reading the problems and see how they want your final answer. Sometimes they may ask for a mixed number or a proper fraction, in which case you'd have to give the answer like this. Or other times they may not care, and they may say an improper fraction is perfectly fine. As we get into more advanced mathematics, improper fractions are used all the time. So we really don't mind them. It's just a matter of preference for that particular problem. A good rule of thumb is usually how you start a problem is how you would give the answer. So if you start with improper fractions, then usually they accept an improper fraction as an answer. I know here we have proper fractions, but if you start a problem with mixed numbers, usually they like mixed numbers as an answer. So just read carefully there as you're going through. Okay. Now we can also do some examples here with variables. So let's say I had something like 9/10 x plus 1/10. So we can go ahead and do that too. I have the same denominator here. So I can go ahead and add. You just want to be careful. It's not 9 plus 1 is 10. It's 9x. So this x gets tagged on with the numerator. So 9x plus 1 over 10. So again, we just want to be a little careful there, as that's kind of tricky to see that like that. So if I see something like, how about, hey guys, I'm having quite the day here. My internet just shut off for a second, so I apologize. Let me get my screen back up here. All right, so what I was trying to say here is that when we're subtracting, even if we have common, those like fractions, so those same or common denominators, when you have a variable like this, if it's next to a fraction, it's actually in the numerator as well. So we can bounce back and forth, where something like 7x over 8 is the same thing as 7/8 x. If the fraction has the x in the denominator, this will be very clear. It'll be clearly in the denominator. So if it's just kind of hanging around, it is in the numerator. So when we subtract, it would be 7x minus 4 all over 8. And because these are unlike terms, then we can't combine them any further. So it's not 7 minus 4 is 3 and this becomes 3x. It doesn't work that way. You have to still think about like terms. If I had something instead like 7x over 8 minus 4x over 8, well, now I have 7x minus 4x, and these are like terms. So now I can go ahead and subtract. So again, you just want to be careful here as to what kind of problem do we actually have. Okay, so let's do a different style problem with variables. So now we're doing our evaluating. So our expression is y minus x. So the y value is going to be negative 8/10. That gets plugged in first, minus, and then our x value is negative 3/10. And I'm just using parentheses here to help me. I actually could put them here as well. This is a subtraction problem though. So if I rewrite this, this turns us to addition, and then my negative becomes a positive, right? Because we do that keep, change, change. Now I have negative 8 plus 3, which is negative 5 over 10. And you do want to simplify. So I am noticing that both of these are divisible by 5. So I have negative 1 over 2. And remember, a 1 in the numerator has to stay. We can't get rid of it. We only can cancel out 1s in the denominator because that's dividing by 1. And one last example here, just to bring in a real world application. So let's say I have a rectangle, and maybe my width is 2/7 inches. And then my length maybe is 6/7 inches. I could ask a question like, find the perimeter. So this is a nice review. Remember, perimeter means to add up all the sides. So we'd have 2/7 plus 6/7 plus another 2/7 plus another 6/7. And because these are all like, we can just go ahead and add up the numerators here. So I have 2 plus 6, which is 8, plus 2 is 10, plus 6 is 16. So I have 16 over 7, and this is still inches. And again, if you want to change this over to a mixed number, we can. I do know that this is simplified, though. 7 is prime, and 16 does not have any factors of 7. So I do know that this is simplified. If I want to change this over, it does go in 2 times, which is 14. So I can write this as 2 2/7 inches as well. Okay, so when we already have like fractions, we can add or subtract pretty quickly. It's pretty straightforward, where we keep that denominator the same, add or subtract with a numerator, and then if we can, we still simplify, right? So at the end, you're always going to check to see if you can simplify those final answers here. Now, if you don't have common denominators, that's when it gets a little trickier. So that's what the next part about this video is going to be about, okay? So if we do not have like fractions, we need to create equivalent fractions so that they are like. And to do that, what we need to do is to find a common denominator to use. And remember, the word common really means the same. So we want to make sure that we create fractions such that they now have the same denominator, and we can go ahead and add or subtract. So that's what we want to do. We usually like to find the least common denominator. We abbreviate that LCD just to save ourselves some writing. And that is the smallest denominator in common to all fractions. All right, so let's think about different ways that we can do this. So we actually have 2 different strategies that we can use here. So the first idea is to use multiples to find the LCD. This is actually my preferred method. I think this is the easiest one to use, although sometimes it can be time consuming, but we can do it. So it's easiest to do it also with an example. So let's do an example. I'm going to use 1/3 and 4/15. Now these clearly are unlike fractions, so we want to be able to make them like. That's our goal, is to make them like. And the first step there is to figure out how to find the easiest denominator to do that, and that's your least common denominator. So what you do is you're going to list the multiples for each denominator and find the first one in common. This is actually called the least common multiple, or we'll say LCM. All right, so my first denominator is 3, and then my other denominator is 15. So we're going to write our multiples out. So what you do is you multiply by 1, you multiply by 2, by 3, by 4, by 5, by 6, and so on. So I do 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15, 3 times 6 is 18, 3 times 7 is 21. And I'll stop there. Then I do the other one. 15 times 1 is 15, 15 times 2 is 30, 15 times 3 is 45, 15 times 4 is 60, 15 times 5 is 75, and I have 90, 105. And again, I'm going to stop there, but you can go on as long as you need to. And what you're looking for is the first number in common. So if I look through my list, I see that they both contain number 15. This is the first one in common. So my least common multiple here is 15. So this means my least common denominator is going to be 15 as well. All right, let's try another example. And we'll do this one in blue. So I'm going to do 5/6 and 1/5. Now, again, these are different fractions, right? They're unlike. So I want to find what would be the easiest denominator for me to change these over to. So that's called the least common denominator. So I'm going to take my denominators. I have my 6, I have my 5. I'm going to go ahead, I'm going to multiply them by 1, by 2, by 3, by 4, by 5, by 6, by 7, as many as you need to get one that matches. So 6 times 1 is 6, 6 times 2 is 12, and I have 18, 24, I have 30, 36, and 42. Here I have 5 times 1 is 5, 5 times 2 is 10, times 3 is 15, then I have 20, 25, 30. I'm going to stop because I do see a match. I see that 30 in common. So my LCM here is 30, which is also the same thing as my LCD. So your LCD is just the least common multiple for the denominators. That's all it is. It's really the same definition. Just that D means specifically using the denominator values. Now, you can use this strategy for as many fractions as you want. So if you had 3 fractions here, I would make 3 rows, and then I could go ahead and find the one that's in common for that, for instance. Right? So let's say I wanted to add in the fraction 1/10 here. Then I would just do another row. So 10 times 1 is 10, 10 times 2 is 20, 10 times 3 is 30, and I still see that the first number in common is 30 to all of them. So 30 is the least common denominator for these 3 fractions. Okay, so that's the first way you can find the least common denominator. For me, that is my favorite. I think that is probably the easiest way to do it, but it does get complicated for large numbers. That's the only problem. If you have really large numbers, then those multiple lists can get pretty tricky, particularly if you're not using a calculator, right? And we're not using a calculator right now, so they can be hard. So another way to do it is using prime factors. So this is the second strategy to do the prime factors. So and I'm going to use actually the same example here. Okay, so what you're going to do is you're going to write the prime factorization for each denominator. That's going to be your first step. Okay. Then you're going to basically combine those two prime factorizations together, making sure all factors are included. So I'm going to write like this: combine the two factorizations, making sure all factors are included. And then the LCD is this combination. All right, so let's try this out. I'm going to start with both of my denominators. So for 3, I don't actually have to do anything. 3 is already prime. But for 15, I can break that into 3 times 5. So for the number 3, my answer is 3. And for the number 15, it's 3 times 5. So what you're going to do for the LCD is you're just going to put all these factors together. So usually what I do is I'll take one group first, and then I'll add in whatever's missing. So if I take my first group, I see that I have the 3 here. So I'm going to incorporate the 3. Now for 15, I already have a 3, but I already have it included, so I don't need to write it again. But I do have a 5. So our LCD is going to be 3 times 5, which is 15. Let's do the other example. So the other example was 5/6, 1/5, and 1/10. So if I do 6, that's 2 times 3. If I do 5, 5 is already prime. And then for 10, it's 2 times 5. So I'm just going to write these out. So for 6, it was 2 times 3. For 5, it's just 5. And then for 10, it's 2 times 5. So for your LCD, again, how I like to do it is I'll just take the whole first one. So I'll take the 2 and I'll take the 3. Then I look at the next one. Well, this one's a 5. I don't have a 5 included yet, so I'm going to take the 5. And then I go to the next one. I have a 2 and a 5 here. Well, I already have a 2. I don't need another one. And I already have a 5. I don't need another one. So my LCD here is 2 times 3 is 5. So that's 6 times 5, which is 30. All right. Let me do one more example here that's a little bit harder so you can see this one in action. So let's do So we're going to find the LCD of negative 23 over 72 and 17 over 60. Now, this is one where the first strategy, writing all the multiples out, is probably going to be really tough, right? These numbers are pretty large. I know for myself that 72, I don't even want to multiply it by 2, by 3, by 4. It's just going to take me a really long time. So this is a good one where maybe the prime factorization strategy is easier. So I'm going to start by taking my 2 denominators and break them down into their prime factors. So for 72, let's see, that would be 8 times 9. And then 8 is 2 times 4. 4 is 2 times 2, and then 9 is 3 times 3. And then for 60, I have 6 times 10, so which is 2 times 3, and then 2 times 5. So for 72, my prime factorization is 2 times 2 times 2 times 3 times 3. And then for 60, it's 2 times 2 times 3 times 5. So again, how I like to do it is I'll take the whole first one. So I need everything here from the first one. So 2 times 2 times 2 times 3 times 3. So I take all of these. And then I check the second one and see if I'm missing any. So this one matches with this one matches with this one, and this one matches with this one. So those all have a match. Now I don't have a 5 though, so I am going to have to multiply in that 5 as well. And now I go ahead and multiply this all out. So 2 times 2 times 2, this is going to be 8. 3 times 3 is 9, and then times 5. So I'm looking here at 72 times 5. Which is 360. So that would be my LCD in this case. The smallest possible value that I can get to put these two denominators and make them the same is going to be 360. So the prime factorization strategy, although it's not my favorite, I'm not going to lie, I really prefer the multiples one, is very good when you have large numbers. It just gets to be really too cumbersome sometimes to try to go through all of these. Okay. And then maybe let's just do one more of these because these can be kind of tricky. All right, so again, these are some larger numbers. I don't know if you really want to do multiples for 18 and 54. It gets to be kind of cumbersome if you're not using a calculator. So we'll do the prime factorization method. So 18 is 2 times 9, and then 9 is obviously 3 times 3. And then, so for 54, this one, what we could do, let's see, if you're not familiar, you could divide this by 2 because it is even. Or I can notice that this is 6 times 9, which is 2 times 3, and then 3 times 3. So for 18, I have 2 times 3 times 3. Then for 54, I have 2 times 3 times 3 times 3 again. So I'm going to take the whole first one. So I have a 2, I have a 3, and I have a 3. Because again, we need all combinations of these factors here. And now I'm going to see what I have left. So this 2 matches with this 2. This 3 matches with this 3. And this 3 matches with this 3. So all of those factors are already included. But I have an extra 3 hanging around that I haven't matched with. So I do need to include this extra 3. And if I multiply this all out, I get, let's see, 2 times 3 is 6, times 3 is 18, times 3 is going to be 54. So my LCD here happens to be 54. Now we can also extend this idea to variables. And again, when you get into tougher ones, the prime factorization I think does work a little bit better. These actually are pretty nice because 5 is already prime, but I do have these variables to break down. So I'm gonna skip the tree part because I don't really need to do a tree here with the number 5, but I am still gonna write down all my factors. So that x cubed is x times x times x. So for my LCD, I always take the first one in its entirety. So I'm going to take the 5. Then I go to the next one, and I say I have an x here. Well, I don't have any x's yet, so I need to take that whole one too. And then I go to the next one. And now I can say, okay, well, I've already taken one x. I don't need that x. But I do have 2 more x's here that I have not accounted for, right, in my LCD. So I'm going to go ahead and tag in these 2 x's. and then x times x times x is x cubed. So I can also use this strategy when working with variables as well. All right. So it's your choice which strategy you like. Again, I prefer the multiple strategy in general, but for harder problems, sometimes that prime factorization can definitely be the way to go. So now the whole point of this is actually to go ahead and learn how to write fractions with common denominators. So let's take it that next step. So let's do some examples here. Let's do write 3/5 as an equivalent fraction with denominator 20. So I'm going to save a little bit of time to start, and I'm going to say we already found the best denominator to use, and it's going to be 20. So how do we change that fraction over so that it has a denominator of 20? And you can do it in different ways. So I like to set mine up this way. I have my original fraction, and then I have my new denominator. And then I think, well, how do I get from one to the other? So to get from 5 to 20, you would multiply that by 4. And it's always going to be multiplication or division. And to get from 3 to what number, you're going to make the same change. So we're going to multiply by 4 here and get 12. Okay, so we need to make the same change to both the denominator and numerator. Okay, so that's a really important idea here. Let's do another one. Right? 3/5 again as an equivalent fraction with denominator 60. So I take my 3/5, I set it equal with denominator 60, and I say to myself, how can I get from 5 to 60? Well, 5 times 12 would be 60. Now, when we're doing equivalent fractions, it should always be an easy transition. It shouldn't be like a decimal or anything like that. So it should be maybe not obvious, but it should be a factor that is going to work. So I make the same change on top. 3 times 12 is going to be 36. So 36 over 60 is the equivalent fraction. Remember, equivalent fractions have the same value. So these are the same exact value. If you were to put both of these in your calculator and get the decimal answer, they're going to match. If you were to draw the pictures, they would match. So these are the same value, just with a different denominator. All right, let's see what's next on my example list through my notes. Right? An equivalent fraction with the given denominator. All right, so this one's a little tricky now. So how do we change that whole number of 4 into something with a denominator of 6? So the first thing you want to remember is that we can always, always, always place a whole number over 1. So I'm going to go ahead and fill that in because dividing by 1 doesn't change anything. So now, how do you get from 1 to 6? Well, I would multiply that by 6. So I make the same change on top, and I get 24. All right, let's just do a couple more here. Again, we're going to write an equivalent fraction. I'm going to give you the denominator. All right, so now I want to go from 3x to 24x. Keep in mind, the x and the x are the same. So the only thing that's changing here is the 3 to the 24. So how do you go from 3 to 24? Well, you multiply by 8. 8 times 8 is 64. Okay. Now again, I'm kicking it up a little bit here. So think about the numbers first. How do you get from 4 to 16? Well, you would multiply by 4. 4 times 4 is 16. But I'm missing an x. So what you could also do is instead of just multiplying by 4, you make this little circle here. You multiply by 4x. And you make the same change on top. Well, 5 times 4 is 20. And then you have the x. Okay, so we can also use these same rules with variables. Now, I want to do one last example, and we're going to do a lot more of this in the next video. So I'm just going to do an intro here. But let's go back to one of those ones we've already kind of done. So I'm going to do this example right here when we were finding the least common denominator, 1/3 and 4/15. So I'm going to say, let's write as equivalent fractions. And we had 1/3 and we had 4/15. So now I'm not giving you which denominator to use. You have to find it yourself. So in something like this, your first step is going to be to find that least common denominator. And we already did it here. So in this case, our LCD was 15 because we already did this example. And then you're going to convert each fraction over using the denominator of 15 in this case. So whatever your LCD is. So let's do it. I'm going to take 1/3 and I want it to have a denominator of 15. And I'm going to take 4/15 and I want it to have a denominator of 15. So in the first case, going from 3 to 15, I would have to multiply by 5 there. So I make that same change up top. 1 times 5 is 5. Now notice that each fraction changes in a different way. This one actually doesn't even change. 15 times 1 would be 15. So 4 times 1 would stay 4. So now I have equivalent fractions, and now hopefully you can see where we're going to go with this. We can actually start adding and subtracting them because now I have a way to make them like. So this is what we're going to do in the next video. So we're going to keep going with this idea. It's really just a continuation. Now that we know how to find our LCD and our equivalent fractions, let's go and practice converting them over and learning how to add and subtract unlike fractions.